Hello everyone and welcome to this course on nonlinear optics. Nonlinear optics is a really exciting branch of physics, and in this course you are going to see some fascinating phenomena, many of which might feel a little unintuitive at first, but that's exactly what makes them so interesting. What I find most exciting is that it's not just about the physics. We'll also be exploring practical applications that are built on the principles of nonlinear optics, things that directly connect theory with real world technology. So, throughout the course, we will strike a balance. We'll dive into the fundamental physics, but we'll also discuss the engineering side and how these concepts show up in practice. Before we go any further, a quick introduction about myself. I'm Abhigyan from the Indian Institute of Science. I'm a Prime Minister's Research Fellow at the Center for Nanoscience and Engineering, and I'm also affiliated with the Department of Instrumentation and Applied Physics. Nonlinear optics is really my bread and butter. My research is centered on it, and that's why I'm especially excited to share this subject with you. I have worked on a wide range of fields, starting from fiber laser, nonlinear optics to some biomedical imaging technology like photoacoustic imaging, and in the semiconductor field as well. Here is my website link. You can check this out for research areas and other information. And also, I'll be uploading lecture materials to this website. Now, in today's lecture, we will keep things light. It will mostly be an introduction. From the next class onwards, we will begin building the deeper concepts step by step. But I actually think the best way to start is by looking at some real life applications of nonlinear optics. That way, you will immediately see why this field matters and why we should care about it at all. So let's get started with some of the most exciting applications that nonlinear optics makes possible. Before we dive deeper into the principles of nonlinear optics, let me throw in one important fact, that is, nonlinear optics becomes evident only when the electric field of light is very strong. We'll unpack this in detail later, but for now, just keep this idea in mind. And where do we get such strong electric fields? From lasers, right? So, what I work on is something called fiber laser. That's a laser technology. Have you heard of fiber laser before? If not, that's completely fine. Let me introduce you. Now, I'm guessing most of you already know the basic ingredients of a laser. First, there is a gain medium where we create something called population inversion. Basically, more electrons in excited states compared to lower energy states. The gain medium could be many things, a crystal, a ruby rod, a rare earth doped glass, and so on. On top of that, you need feedback. Typically, this is achieved with two mirrors, one fully reflective, one partially reflective, to bounce light back and forth. Now add in pumping to excite the gain medium, and once you cross the stimulated emission threshold, you get a laser output. That's the generic laser. Now in a fiber laser, the gain medium is not the crystal but a rare earth of optical fiber, and instead of traditional mirrors, we use something called fiber Bragg grating. One fiber Bragg grating is highly reflective, the other one is partially reflective, so it acts as the output coupler. The pump light, usually from a diode laser, is injected into the fiber through a pump combiner, which is basically a device to couple pump light efficiently into the gain fiber. That's the basic structure of a fiber laser. So, why do we care so much about fiber laser? Well, here is a fun fact. The very reason you are able to listen to this lecture today is because of fiber laser. How so? Fiber laser are at the heart of our internet infrastructure, the signals that make global communication possible. Zoom calls, YouTube videos, even online courses like this one travel through optical fibers across continents. As the signals travel, they weaken and they need to be amplified. Fiber lasers, specifically RBM doped fiber amplifiers, are the backbone technologies that makes this signal regeneration possible. Here you can see a map of the global fiber optic link network. These connections are actually laid out through oceans across continents, and this image is freely available online if you'd like to explore it further. What's really fascinating is that all of our internet traffic, emails, video calls, streaming, and everything is traveling through these undersea fiber optic cables. In fact, here's a picture of one such cable lying on the ocean floor. That's the real backbone of internet infrastructure. So, the very technology that carries our digital world is rooted in optics, and that's where our journey into nonlinear optics connects back in a very real way. So, when we study fiber laser in the context of nonlinear optics, we are not just learning abstract physics, we are looking directly at the technology that makes modern communication and, in fact, much of modern life possible. Before we really dive into how nonlinear optics comes into play in the context of fiber laser, let's first take a step back and look at some of the existing fiber laser technologies. The idea is simple. Once we understand how what kind of fiber lasers are out there and what limitations they face, it will become very clear what specific problems nonlinear optics can help us solve. So let's start with a quick overview of the different fiber laser platforms, and then we will see exactly where nonlinear optics becomes essential. On this slide, you can see the typical operating wavelengths of different rare earth doped fiber lasers. Ytterbium doped fiber lasers work around the 1 micron region, that's wavelength I'm talking about. Erbium doped fiber lasers give emission around 1.5 micron, and thulium and holmium doped fiber lasers operate near 2 microns. But here is the problem. What if we need a laser at a wavelength that doesn't match any of these dopants? For example, suppose I want a laser source around 1200 nanometers for a specific application. We simply don't have a gain medium that directly emits at that specific wavelength. So, what do we do then? This is where nonlinear optics comes to the rescue. I want to introduce to you the first nonlinear effect in this course, that's Raman scattering, or more specifically stimulated Raman scattering. And this effect is the foundation of something called a Raman fiber laser, a type of laser that can generate output at essentially any wavelength you want. That's pretty exciting, right? It's one of the reasons Raman fiber lasers are so powerful and versatile. And here is also a bit of history that makes it even more interesting. Stimulated Raman scattering is closely tied to the discovery of Raman scattering, first observed by C.V. Raman, the first Indian director of Indian Institute of Science, my own institute. His discovery of Raman scattering won him the Nobel Prize in Physics in 1930, and it laid the foundation for this entire field of research. So, what exactly is Raman scattering? Let's start simple. Normally, when light interacts with a medium, most of it comes out with the same frequency as it went in. That's what we call elastic scattering. But a very tiny fraction of light interacts differently. It exchanges energy with the vibrational modes of the molecules in the medium. This is called inelastic scattering, and the scattered light comes out at a different frequency compared to the input. This shift in frequency is what we call Raman shift. If the photon loses energy to the medium, we get what's called a Stokes shift. Hence, we get longer wavelength. This Stokes shift frequency is shown by capital omega r in this slide. If it gains energy from the medium in a different instance, that's an anti-Stokes shift, or we get shorter wavelength at the output. This is not what I am showing in the current slide. Now here's where it gets really useful for lasers. In an optical fiber, if we pump the medium strongly enough with a high power laser, this weak Raman scattering can get amplified through a process called stimulated Raman scattering, and this SRS effect can convert light from one wavelength to another. That's not restricted by the electronic transition of a gain medium. This is the principle behind a Raman fiber laser. By carefully choosing the palm wavelength and allowing multiple Raman shifts, we can generate laser light at wavelengths where no traditional doped fiber laser exists, like that of 1200 nanometers example we talked about. In fact, by cascading multiple Raman shifts, we can cover a very broad range of wavelengths almost continuously. So to summarize, conventional fiber lasers give us only fixed wavelength bands like 1 micron, 1.5 micron, 2 micron, etc. On the other hand, Raman fiber lasers give us the flexibility to access almost any wavelength thanks to stimulated Raman scattering. So the specific kind of lasers that I work on is Raman fiber lasers. The way it works is we start with a high power fiber laser source. In most cases, that's an ytterbium doped fiber laser, the way I am showing in the current slide. Now, when this laser light propagates through an optical fiber, it undergoes stimulated Raman scattering, which transfers power from pump to a slightly longer wavelength, one Raman Stokes shift away. That newly generated wavelength can itself act as a pump, transferring power to an even longer wavelength, and so on. This process, called cascaded Raman shifting, allows us to generate a wide range of wavelengths, all starting from a single high power fiber laser source. And that's the beauty of Raman fiber laser. They give us tunable access to wavelengths that conventional fiber lasers simply cannot provide. That's not the end of the story. All the wavelengths I have been talking about so far, 1 micron, 1.5 micron, 2 micron, they fall in the infrared region, which means they are invisible to the human eye. But what if I actually want a visible laser source, something like green or red light? How do we do that if our gain media only gives us infrared? This is where I want to introduce the second nonlinear phenomena in our journey, second harmonic generation, or SHG. This is what we call a Chi2 process, a second order nonlinear process. The Raman scattering I was talking about is a Chi3 process, a third order nonlinear process. Don't worry too much about the order yet. When we dive into the theory later, I will explain exactly what second order, third order, and so on mean. For now, let's take it as a label. So what happens in second harmonic generation? In simple terms, using a nonlinear crystal like I'm showing in the current slide, we take the incoming wavelength and halve it. Equivalently, you can think of it as doubling the frequency. For example, a 1060 nanometer infrared laser can be converted into 530 nanometer, which is bright green. A 1400 nanometer infrared laser can be converted into 700 nanometer, which is red, and so on. Invisible infrared light gets transformed into brilliant visible colors. Now, instead of just talking, let me show you a demonstration. Here you can actually see the process happening. A 1060 nanometer laser converting into green, and as we tune further, what I am tuning I will tell you later. As we tune further, you will see it changing across the spectrum: green, yellow, orange, red, and even beyond into the infrared again. We will come back to the detailed theory behind this when we reach the Chi 2 chapter, but for now I want you to appreciate how beautiful and practical this nonlinear phenomena is. So now that you have seen some exciting applications, let's step back and build a solid physical foundation for nonlinear optics. The first question is, what do we really mean by nonlinear? Well, let's start with something simple. If the system is linear, it follows the principle of superposition, which means if input A produces response X and input B produces response Y, then putting A plus B will give us exactly X plus Y. No surprises, no extra terms, that's linear. On the other hand, if the system is non-linear, things don't add up so neatly. If I put in A plus B, the output is not just X plus Y. New responses will appear, things you couldn't get from either input alone. That's the heart of non-linearity. Now let's bring this idea to optics. In optics, the central relation we care about is between electric field of light and the polarization of the medium as it passes through. In a linear material, polarization is directly proportional to the electric field. That is, polarization is equal to epsilon naught chi 1 times electric field. Here chi is the linear susceptibility. It tells you how easily the medium polarizes in response to the input electric field. But when the field is very strong, like with a laser, the medium can't just respond linearly. The polarization now has extra terms, like polarization is proportional to epsilon naught chi 1 times electric field, but it's also proportional to epsilon naught times chi 2 times square of the electric field, and also it's proportional to epsilon naught chi 3 times cube of the electric field, and so on. These higher order terms like chi 2, chi 3 and so on are what gives rise to nonlinear optical effects. Like second harmonic generation that we talked about, that was a chi 2 process, and Raman scattering we just saw, that's a chi 3 process. So in summary, linear optics is what you have mostly studied so far and what you observe in day-to-day life: refraction, reflection, interference, diffraction, etc. And nonlinear optics kicks in only when the fields are strong enough, and suddenly new frequencies, new interactions, and all kind of surprising effects appear. That's what makes this field so fascinating. In your day-to-day life, almost everything you see related to light is the result of linear optical phenomena. Think of reflection, refraction, absorption, or even simple scattering in the sky. All of these are governed by linear optics. Here's an easy way to picture it. Suppose you are holding a glass and you shine a green laser through it. What do you see? You only see the green beam coming out. The frequency or the color doesn't change. That's what linear optics does. It preserves the frequency of light. But in nonlinear optics, something much more interesting happens. Frequencies can actually change. That's when you start to see all sorts of beautiful, surprising phenomena, like the frequency doubling I showed you earlier in the demonstration. And here's a fun trivia for you. Whether you realize it or not, all of you have probably used a nonlinear optical device at some point. Any guesses? It's a green laser pointer. Now, here's the secret. The actual laser inside the pointer is not green. It's an infrared laser that's invisible to your eyes. The green you see comes out from a nonlinear crystal inside the device, which doubles the frequency of the infrared light, and that's how you get a bright visible green beam. So the next time you pick up a laser pointer, you will know you are literally holding a nonlinear optics experiment in your hand. So we will dive into the detailed physics of all of this starting in the next class. But before we wrap up today, I want to give you a bit of history just to show you how nonlinear optics grew up into such an important and exciting field in this century. The story begins, as I mentioned earlier, with C.V. Raman right here in India. There are lots of other nonlinear phenomena also discovered around the same time, but I'm just starting with um, Raman scattering because I have introduced to you in the earlier slide. In 1928, he observed the phenomena of Raman scattering, and the discovery earned him Nobel Prize in Physics in 1930. This was really the first of the many steps into the world of nonlinear optics. And after that, the progress was quite slow. And why? Because nonlinear effects demand very high intensities, and at that time, such light sources simply didn't exist. The field had to wait for a new invention. That breakthrough came in 1960 when Theodore Maiman built the first laser. With lasers, suddenly the intensities required for nonlinear effects became possible. And then in just very next year, 1961, the first second harmonic generation was observed. From that point, the field just exploded with new discoveries. Fast forward to today, nonlinear optics has expanded into areas like quantum nonlinear optics, ultrafast optics, and so many advanced applications that impact communication, imaging, and even fundamental science. So that's the journey in a nutshell, from Raman's discovery to the birth of lasers to today's cutting edge research. We'll explore the details, the math, the physics, and the applications in the upcoming classes. Thank you for attending today's session, and I'll see you next time.